recording. I've started the recording. Okay, Ronak. So, welcome, Ronak. Good afternoon. So, where are you from? So, you're MSc, BSc, PhD student. What are you pursuing right now? Okay, nice. So, let's wait for few minutes. Because there might be some people, some other student going to join. Mhm. So, have you watched the lectures? So, how many lectures are there in first week? Six or five? Okay, okay. So, how many assignments have already published? Okay. So, have you solved the week 0, week 1, both of them, both the? Okay, okay, no problem. So, you are BSc third year. Oh, you are in BSc first year. Oh, okay, nice, nice, nice. So, like recently, last year or last to last year, you have passed your 12th. Okay. Then it must be little bit advanced course for you. I believe so. Mhm. Okay. Yeah, yeah, yeah. So, are you giving the exam for this course or not? Mhm. Because I am seeing that not many people have student have giving the exams. They have not registered for the exams. Only few of them have registered for the exam. So that is why I thought. So it will be so in your BSc first year, any teacher or any course is there who is teaching this basics of fluorescence in your college? Okay. So welcome Lavanya Kali Gupla. Okay, there's someone else Balaji. So welcome Lavanya, welcome Balaji. So where are you from, guys? Lavanya and Balaji. Yes, Lavanya, tell me. Yeah, yeah, there is a, yeah, your video is not visible, so it is not a problem, but you can speak. So basically, I want to know that how many students are there and what they are doing. Just like Ronak just said, he is in first year BSc. So Yes. So you are in, what are you pursuing? Okay. So you have not done this course before, or you are here for the certificate? So you don't have any basic knowledge of this fluorescence spectroscopy or what? Okay, okay. And what about Balaji? Okay. So you are, so why professor is taking? Because he is not from fluorescence background, or he's from some other background? Oh, okay, okay. Pharmacy. Okay. So you are doing B Pharma. Okay, okay. 4 year or third year, 3 year program. So okay, okay, okay. It is 4 year program, no? B Pharma. Okay. So you are in fourth year. Okay, okay. Nice everybody. I have, like, not too many people are here, but I can see only few. Okay. Bhupendra Singh, it is me, Balaji Bhupendra Singh. I am presenting my presentation from my iPad. Lavanya is there, Patlika is there. I have already interacted with her. Shiv Mathur, I have interacted with her before Ronak. So one, two, three, four, five of you are there. Okay, so have you solved? Have you? I have already asked Ronak and other, Lavanya and Balaji. Have you watched these videos, first week videos, and solved the week 0, week 1 questions? Okay. What about Balaji? Okay, okay. No problem, no problem. You can ask. We have time. Like, it is, this session is going for 2 hours, so you can ask any time. But so it will be better if I solve all the questions one by one. So let me first, okay, this will not go. Yeah, slides are you guys able to see my slides are changing? Okay, okay, fine. Then this is, okay, so let me introduce first myself. My name is Bhupendra Singh. I'm fifth year PhD student at IIT Kanpur. I'm working under the supervision of the instructor of this course, Professor Pratik Sen. So I will be teaching you around 8 to 9 live sessions for 2 hours. So it will be 18 hours total, and I will be solving all the this year's this year uh, questions, assignment questions, also the previous year assignment questions. So it will be better for you guys to actually um, understand and solve, because I think you are able to access only this year's questions, but not the previous year questions. Okay. So this is little bit introduction about myself and the course. So this course is all about the fluorescence spectroscopy. Whatever instructor have taught and assignment has been given, we will discuss. And in between, you are free to allow to interrupt me, ask questions, and when I am solving some question, if you have any doubt, you can just anyway, so this is mm, anyway. So this is assignment week 0 question. Week 0 assignment है this one. So first question is spectroscopy is fundamentally defined as the study of. So I believe this much you have already understood. That is, yeah. So spectroscopy is the study of interaction between radiation, this is the light, and the matter. Matter means. Can you switch off your microphone? Yeah, yeah. Thank you. So radiation spectroscopy is the study of the interaction between the light and the matter. Light, light is sunlight, just like the sunlight, which have um, wave-like nature and the particle-like nature, as de Broglie have mentioned. So, what is matter? Matter is, in our case, matter is any molecule or any biological macromolecule or any small molecule, that will be the matter, or any nanoparticle. So these are the matter in our case. So when the light falls on the surface of, or on the molecule or any matter, what happens is that this light, many phenomena can be there, like it will maybe reflect, diffract, or it will transmit, it will absorb. After absorbing, it will fluoresce. So basically, if that interaction will happen, and we observe that interaction between light and the matter, that is called the spectroscopy. So uh, the answer for this one is the interaction between the light and matter. Okay, option C. So this much, I guess nobody have any problem, right? Yeah, yeah. So and also we will have the this interaction. When I am going to ask you something, you can just unmute yourself and say yes, no, and you have understood, not understood. There is no problem. You can just say. So it will be, if it will be good if we have interactive session. Otherwise, I will be like a um, just giving you the lectures. So that will be better for you to understand. Okay. Anyway, moving on to next question. Next question is the molar extension coefficient. So first option is independent. So first we have to know the, this is all I have already actually given you the note. This is the first lecture PDF, the screenshot. So we know this formula, right? How many of you are familiar with this formula? Ronak, Lavanya, Balaji, Shivam, Patlika. Yeah, yeah, yes. So this is your absorbance, OD. This is Lambert-Beard law. Yes, Lambert-Beard law. Okay. Lambert said that the, so absorbance is that when the light is falling on the matter, what will happen? The electron will absorb the energy and will move to the excited state. Just like this. Let's say I'm going to the atomic level. Let's say this is your atom, this is the nucleus. Here positive negative charge is there, neutron and not positive negative, only positive, neutron and positron, proton, sorry. And then this is your cell, let's say KLM. You can choose different color. Let's say here two electrons were there, another electrons were there. So anyway, when light is falling, when light, let's say this is the light, is falling on this, what will happen? This electron will absorb the energy and then move to next level, higher excited state. In spectroscopy, what we represent? We represent like this. This is your ground state, let's say. This is your excited state. So this electron or molecule, we generally say molecule. We don't. It is only the electron is, of course, electron is absorbing. Electron is going from the ground state to the higher state. We normally call molecule. So molecule after observing is going to the higher state. So this is the higher state. Higher state, I am choosing another color. Let's see, this is higher state. After observing. So now are you able to relate these two? These two. I need to choose another color actually. Anyway, this and this, these two. Any relationship, any commonality, are you able to understand why I have drawn this and this? Yes, this is because I'm trying to give you the picture of the electronic transition. So this electron is this S0 and S1. This is your ground state. Ground state. This is your excited state. Here, by looking at this atom, this is your oh, mm, this one. Okay, this is your this is your this one. This is your oh, too difficult to write. Anyway, this is your exact. My this is your I don't know why it is not working. Anyway, I'm taking new slide. If someone want to join, okay. So this is S0. If this is not working, I have no clue. Oh, I'm struggling to write. I don't know why this is not working today, but anyway. Uh, Anyway, I have drawn here S1, S0, S1. So this is ground state and excited state here. So that is why. So are you able to relate these two or not? So the molar extinction coefficient, yeah. So the molar extinction coefficient is independent of wavelength. A, B depend on temperature only. C is a function of wavelength. D is equal to the absorption cross section. So according to this formula, another formula is there also. This formula in this here, in this formula, this. Oh, bhai, this formula. This one. So according to the, the option D is equal to the absorption cross section. So this is the absorption cross section sigma. So sigma equals to 2.303 epsilon CL. CL. This is your absorption cross section. This is too thick anyway. This will go anyway. So the option D was is equal to the absorption cross section. This is your absorption cross section. This is your molar extension coefficient. So it is not equal to. It is written equal to. They are related. They are in fact they are directly proportional to each other. That is true, but they are not equal. Fine. So D is not there. D is the wrong answer. Next, so D is then depends only on temperature. There is in the formula, both the formulas, there are no role of temperature. Of course, there is a role of temperature, but for the time being, I'm saying there is no role of temperature because in this formula you are not seeing temperature term anyway. So this is also not correct. Option A is independent of wavelength, but in actual, if you have learned this, then you have seen this here. This epsilon is depend on the wavelength. So basically, whenever we observe, whenever we whenever we take this, let's say this is your absorption. I'm giving the data. Absorption, this is your wavelength, right? So let's say this is your absorption, and this absorption actually is directly proportional C concentration and length. This is the concentration of the sample. This is the path length. L is the path length, and E is the epsilon. This is the molar adsorption coefficient, which depends on the wavelength. So, what does that mean? It simply means that the this is the molecular property. This that the is not absorbing uh, molecule is not absorbing um, like the efficiency of the absorbing of the molecule is not same at all the wavelength. So let's say at this wavelength, this is lambda 1. Let's say this wavelength is lambda 2. This is lambda 3. This is anyway lambda 1, lambda 2, lambda 3. So I have taken only three wavelengths. In all these three wavelengths, this epsilon value is different, and this is a property of the molecule or matter, whatever in your whatever the sample you are observing. So that is why it is the property of the that is why it depend on the wavelength. So the first option is independent of the wavelength. So this is also not correct. Maybe it will be looking like I am giving you some just without explaining facts, giving you just the facts without explaining. But I hope that you have seen the videos, at least first week videos. Then it will be easier for you to understand whatever I am giving. Okay, okay, I can show you the real data also, because as I have already mentioned, I am doing PhD, so I have given one my data set from my PhD also here somewhere, absorption data only. This is my data. Are you guys able to see this normalized absorption versus wavelength? Anybody? Yeah, yeah, Lavanya is. So this is the actual data. This is the data of the protein. So I am working on protein. I have tagged the protein with some chromophore. Somebody wants to join. Looks like. Okay. So this is the actual data. So normalized absorbance versus wavelength. This is my data. So so the absorption something looks like this. So here there are two chromophores in the sample. First one is because this one is for protein, this one, and this one is for the this fluorescent dye. So this is how it looks like. That is why the intensity of the peak is also different. Of course, this is not only the reason. It depends on many things, that the concentration, because here, okay, let me be very clear. This peak is of CPM dye, and I am working on human gamma D crystalline protein. So this peak is of tryptophan. In my protein, four tryptophan molecules are there. So this absorption is coming because of the tryptophan. So it depends on how many chromophore or fluorophore are present in your sample. Anyway, and and the concentration of that. Anyway, if the concentration is also same, and this only one chromophore is present. Let's say I am considering only this part. Forget about my protein. Only CPM part, which means why I'm talking about the molar absorption coefficient. So why this molecule? Why this CPM? The peak is around here. I would say 395 nanometer. So why the intensity of the CPM dye is higher at 395 nanometer, and it will be lesser if we go right or left side of the 395 nanometer, right? Because in the sample you have the same dye, same concentration. Why? This is one of the reason. It is not solely reason. I am just trying to explain the molar absorption coefficient. That is why I am saying it is not solely reason, but I am giving. So here the molar absorbability at this wavelength, let's say this wavelength is 355, at here 395, and at 500, the molar absorptivity coefficient is depend on the lambda. So now I think I have explained you a little bit. So now tell me epsilon lambda 355 epsilon epsilon what is that 395, and one is epsilon 500. So this is your 1, this is your 2, this is your third. Tell me which one is greater, given that the sample is same, given Lavanya, can you mute yourself? Yeah. So given that the concentration of the sample is same, of course it is fixed, volume is same, concentration is fixed, same sample is there. So out of 1, 2, 3, tell me what is the order of epsilon? Crudely, very crudely, it might not be correct, but whatever I have told you, you should be able to answer this. Anybody? Balaji, Ronak, Lavanya. Uh, so you are saying this one is greater than? Okay. Yes. Why I am not able to write today? I have no clue. This is really creating problem. Anyway, according to you, this is your answer, right? 500 is higher than 395, then 355. Okay. Anybody wants to participate other than Lavanya, of course. Ronak, Balaji, and the new person, Pravalika. It should be taken from the graph, no? That is what I'm explaining. I'm explaining that it depends on the mole. See, look at this formula, no? We are going. Yes. Oof. So according to me, epsilon at 395 should be higher than the epsilon at 355, then epsilon at 500. So this should be the, because you know this formula, epsilon E EM. So I'm telling you this is the same sample and the concentration is same. So it depends upon the absorption only. and this epsilon is depends on the wavelength. So I hope now I am clear. Balaji, Ronak, did you get it? Yeah, because it is important. Okay, moving on. So number two was is a function of wavelength. So this is correct. That is why the option C is correct. Any problem? Anybody? I hope there is no problem. So okay. So option C is correct. So now I hope there is no problem. If you find any problem, maybe you are afraid to ask now, you can come in the next class. You can come in the next class and then ask the questions. Okay, okay, C is the left. No problem. Okay. Next question. The question is the unit of absorption cross section sigma when E is expressed in liter per mole per centimeter is. So basically question is asking for the dimension of your absorption cross section. So anybody have figured it out? What is the absorption cross section? Unit of the absorption cross section. Okay, I know that Ronak have not solved the questions, but anyway, but anyway, uh, yes, it is written there, but it is that you can also see the option is written there. Anyway, but you have this formula, no? This formula is written over there. Today, no clue why this iPad I'm not able to write. So formula is 2.03 epsilon CL epsilon C divided by NCL. So in the lecture you can find it out this formula, both the formulas, and then you can drive this one. So this one is also it is all this one is also is in the lecture, and this is also in the lecture. So by comparing these two, you will get this formula, this one. Okay. So if you calculate the dimension, I'm just doing for you. So L will cancel out, L and L. This is just a number. So what is left? Sigma equal to epsilon C and N. And N is your number of molecules. So per centimeter cube. So which can be represented as C is the concentration and Na is the Avogadro number. So which means that the in as you know, like in 1 mole, how many molecules are there? Anybody? Yes, Avogadro number. So this is Na. Na molecule. So that is why C is what? C is concentration, number of moles. Yeah, everybody is there. Okay, so C is what number of moles? N per centimeter square. Why this 1000 is coming? Anybody? You know how to convert uh, meter cube into liter. So in 1 meter cube, how many liters are there? In simple words, 1 meter is like this much. From this, from this, from my fingers to the shoulder. So it is like 1 meter, like approximately. So one meter cube means you have a cube and all the dimensions are 1 meter. So 1 meter width, 1 meter, so 1 meter height, 1 meter width, and 1 meter is length. So in that cube of 1 meter, so the volume of the cube is 1 meter cube. So how many this like how much this volume in liter will come? Let's say if you want to pour the water, how many liters of the water will come? Uh-huh. No, no, not 1 liter. No, 1 liter is just like 1 liter is, see, this bottle is of 2 ml, 2 liters. So you can figure it out. Like I'm talking about 1 meter. 1 meter is like this from my fingers till here. This is 1 meter. 1000. Yes, 1000. So 1 meter cube equal to 1000, and 1 centimeter is equal to one meter equal to 100 centimeter. This we know, right? So now just convert this per centimeter cube. So what will happen? 1 meter cube, which means 100 centimeter cube. This is equal to 1000 liters. So here 10 to the power 6 centimeter cube equal to, okay, which means 1 liter equal to, which means 1 liter equal to 1000 centimeter cube. And this n is your number of molecule per centimeter square. Per centimeter cube, sorry, not square, cube. So that is why this 1000 is coming in division, because this concentration is always we write in mole per liter. So we have to convert this per centimeter cube to liter or liter to centimeter cube. So that is why this 1000 is coming. Anyway. So now we can substitute sigma equal to epsilon C, and this is C and A, and the 1000 will go here, which have no meaning anyway, and this is just a number. Okay, so it will have the per mole. Yes, this will have per mole. So what is the unit of? I need to take one slide. Keep insert. Okay, sigma equal to epsilon C C C N A. So Cc will cancel out epsilon by Na. Na is the this much amount of molecules per mole in a mole. So unit is per mole, and unit of epsilon is already given, liter per mole per centimeter. So liter per mole per centimeter, and here is the mole inverse, unit of Na. Unit of Na is mole inverse. So mole inverse will go. What is left? Liter centimeter minus 1. As we know from just we have derived this, 1 liter equal to 1000 centimeters cube. So 1 liter equal to 1000 centimeter cube. So just substitute 1 liter. This is 1 liter, 1000 centimeter cube, centimeter minus 1. So this is number. Just leave it there. It will be centimeter square. Correct? So answer would be centimeter square. Is it okay? No? Ronak, your first year, so that is why I am asking you. Yeah, okay, fine. So I hope it will be clear to you. So I am moving to next question. Everybody. Okay. So this is the next question. Next question is the correct order of the increasing energy separation between molecular level. Oh, you are not able to see. Now it is visible. Question number 4. Okay. So the question is the correct order of increasing energy separation between molecular level is. So as I have discussed in one of our previous questions, that this is your ground state. I have written as I have written there S0, S1, right? So these are this is your ground state. S1 is your excited state. So these are electronic excited state. So that is why I have drawn this. These are the, and one of you have said that this is the electronic transition. From here to here it is going, means the electron is going from ground state to excited state. So this is electronic transition. Electronic transition. Okay. Now coming back to this, see electronic level, this is electronic state. So for your understanding, this is I have taken from the class lecture only. So this is the separation between these two. So these are the ground and excited state, whatever you are seeing, these are the electronic state. So separation between electronic state is much higher than, and also in ground state, let's say this is electronic level, but in electronic level there are number of vibration levels, and in one vibration level there are number of rotational levels. So you can see in electronic level these are the vibration levels. Just it is there is 4 are representation, but there are numerous number of vibration level. Also in this one level, let's say this is first vibration level. In this vibration level there are numerous number of rotational levels. So now from this picture, so these are electronic states, these are vibrational states, these are rotational states. So from this you can easily figure it out that the energy separation between the electronic state is higher than the vibrational states. Vibrational states means that energy between these two, let's say these two, or these two, or these two, these two, these two, these two, and the energy between rotational level is Difference between is this one. This much energy only. This much. So now anybody would like to answer? What will be the answer? Answer is already given. Explanation is also given. Just you have to say it loud. That's it. Anybody? Suraj. Yeah, yeah, yeah. Yeah. Option B is correct. Yes, because the electronic states and then vibration is rotational. So this is the separation between the two energy level. Is it fine, Suraj? Sagun? Just say, just give up. Yes, yeah, good. That's right. Yeah, 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 fine. Okay. Okay, I'm moving to next question. At room temperature, a molecule is most likely to be found in which state? What does this mean? Yes. Anybody would like to say anything about this? What you have under? Okay, okay, okay. Let's continue, Lavanya. Tell me, what does this mean? Why room temperature? Oh, are you able to know? Good. But my counter argument is that no, no, not argument. Uh, just want to see how much you have understood. Let's say this is ground state. This is first excited state. This is electronic state, and these electronic state I am making it bold. This is electronic state, excited state, and these are fine vibration levels. Now tell me, you are saying that it will be remain at room temperature at ground state, right? And also at the lowest, lowest vibrational state, right? Vibrational level or state. But tell me why it should not be. This is V0, this is V1, this is V2. I'm saying it will be remain here in V2. Why not? Answer me. Why not? So you are saying that V2 is higher in energy, not little bit of course, that is right. Good. Good. So in good, that is the answer. So basically, in the answer is here only, no? In our previous question, so the difference, as we are talking about the difference, this is V0, this is V1, this is V2. So if there is a difference between two level, which means one is higher, which means one is higher and one is lower. So which means that the V0, I'm talking about the S0, ground state. So V0 is, and so on and so forth, right? So that is why V2 is higher in energy. That is why the difference is coming, no? Yes. Okay. Anyway, okay, so answer of this question is lowest electronic and lowest vibrational level. So answer is C. I hope everybody have understood. I'm moving to next question. If you have any doubt, you can interrupt and ask question. And if you are not, come back in the next class and ask the same question. No problem. There is no problem. Anyway, I'm moving to new question. According to the Frank-Condon principle, electronic transition are. So tell me, how many of you know the electronic transition? Okay, you're not able to see the screen. Okay, I'm also not able to see the screen. Why this is not changing? It is little bit slow. Okay, how many of you know what is Frank-Condon principle? Explain me. Explain me. Uh, like in 2 3 lines. Except then Lavanya, because she is already uh, giving answers. So anyway, she is also welcome to explain, but I want more participants. That is why. Suraj, Balaji, Sagun, Patlika, Shivam, Ronak. Who else is there? Ronak, Sagun. Okay. Anybody? What is Frank Condon? It is written there. You can see the screen also. But I just want to know how many of you have understood and able to explain. Ronak, first year. Explain. Ronak. Yes. So what is the principle? You have understood. I know. That is my next question that you are supposed to answer. That is the question, no? That reason you have to find it in 1 week and come in the next class. I'll ask you the same question to you, Lavanya, and explain it to me. Then I'll explain it to you. I want to see how much you can like figure it out by yourself. Okay, everybody. I'm telling to everyone. This I want to know. This is a good question actually. Is it fine, Lavanya? Yes. And also one more thing. Why if like addition to your question, if the nuclear position of the molecule is not changing, then why it is shifted little bit? Like it is here and this one is here. Mass of the nucleus is always greater than higher than the nucleus than the electron, no? Yeah, that is the reason. Yes. That is the okay. Okay. That is the assumption actually. That is the assumption that nucleus is so heavy. Okay, let's discuss. Let's discuss. What is the mass of the electron? Tell me. And what is the mass of the proton? Not proton. Yes, proton only. Tell me, anybody. What is the? You can Google it also. No, there is no problem. Just we want to learn, so there is no problem. We are not giving exam right now. Your exam is on February or March, so no problem. Tell me what is the mass of the electron? Yes. What is the mass of proton? Okay. 27 kilogram kg. Okay, fine. Let's say I am assuming only the hydrogen atom, right? So which means in the nucleus you have one proton and one neutron and one electron, right? So this is your negative, this is your electron, this is your proton, and neutron is also there. Now tell me, in both the masses, which one is higher? This one is higher. Okay, let's calculate how much it is higher. No, let's forget about neutron for this second, for a minute. Let's forget about the neutron. Let's compare this electron and proton. Take the ratio of these two masses. Except Lavanya, nobody is like working. I guess. Anyway, if we take the ratio of these two masses, I'm taking the ratio of these two masses. So let's say this is the ratio. I'm forgetting this 9.1. I'm just approximating, just giving you something. Just want to tell you something. So let's say this 9.1 is 1. This 1.6 is 1. Then compare. What will be the ratio? 10 to the power minus 31 plus 10 to the power minus 27. These units are gone because I'm taking the ratio. So, oh, okay, 9 you have to take 10. This one. 9 is 10, 1.6 is 1. 9.1 is 10. So here is 10 into 10 into this one. So 27 will be, so it will be 4. So 10 to the power minus 3. If we reverse this order, yeah, so proton ratio, mass of the proton by mass of the electron will be 1000, ratio of these two, right? Till here everybody is fine? Yes or no? Just thumbs up, say yes, no. Sagun, this is for asking the question, raising your hand. Anyway, I got your point that you have understood till here. So the mass of the proton is 1000 times higher than the mass of the electron. Just now we have calculated. That is why it is 1,000 times higher. That is why we assume that when the electronic transition is going on, the position of the nucleus will not going to change. This is the answer. Okay. And but one my question to you guys, that question I have asked before, that I have already discussed and I already given the answer to you. Tell me why this blue parabola and green parabola. This green parabola is little bit shifted rightwards from the blue one. My connection is lost. Okay, I'm back. Right? Hello. Are you able to listen to me, guys? Okay, okay, fine. So, no, I'm giving you one assignment. In the next class, you have to tell me why this delta R is there. If we are considering that our position, the position of the nucleus will not going to change. That is, we have considered the. Have you heard about Oppenheimer approximation? No, I guess so. Nobody have. Okay, okay. Suraj have heard it. Okay. So why he has taken that the nucleus is not changing its position, but still in this figure we are saying that we are like moving this green parabola towards right. So why the difference between this nuclear position? This you have to answer, any one of you, in the next class. Anyway, moving to the question. So Frank-Condon principle says that the electron moves much faster because it is lighter in weight if we compare with the nucleus of the molecule. So that is why the nucleus remains stationary at its position during the electronic transition. Okay. So answer would be C. So far that the nuclear position remains unchanged. And first option C is correct. And slow compared to electron transition are slow compared to nuclear motion. That is completely wrong. Accompanied by large nuclear rearrangement, that is the assumption that the nuclear position is not changing, governed only by the rotational selection rule. No, that is also not correct. So I guess you got the crude idea, but one assignment you have to figure it out why the difference between this delta R is there. Okay, fine till here. Everybody is fine. Okay, move. Okay. So when electronic transition are very fast, that is the 1 femtosecond in one very fast. That the 1 femtosecond is compared to nuclear motion, which is in picosecond. Yes, that is the reason of the Franken this nuclear position. The nuclei is not changing the position. But I am asking why every time when we draw this Frank-Condon, try to explain the Frank-Condon principle, why we make this blue parabola and green parabola a little bit shifted. The difference is there, no? Delta R. See? This its equilibrium position, nuclear position of this parabola is here. It will come here. So there is a difference between which means the nuclear position is different when we excite the molecule. But we are assuming that the nucleus is not changing. So why we are making such kind of? It should be like, it should be like, it should be like here, just here, just here. Nuclear position should not change, even if it go to the excited state. The electron will go to the excited state. That is my question. I think I think you got the question. I hope so. We are assuming that it will not going to change, but in the Frank content we always show like this. Why? Question is this. Anyway, if you have not understood, no problem. Come in the next class. I am moving to the next question. Is it fine? Balaji left because he got bored. Anyway, the primary role of the monochromator in an absorption spectrophotometer is. How many of you know what is monochromator? Not separator, I would say. Separator is different thing. Wavelength selector. Separator means it's like you have white light, like Vivgyor is there, all in white light, all the blue, in all these rainbow, all the lights are there, and you are separating one light out of them. But it is not the case. You are selecting one wavelength. Others are present, but you are just selecting only one wavelength. So that is wavelength selector. And that wavelength only pass through this monochromator. Just like in this figure, here it is the lamp. This is the lamp. Let's say I am saying this is the sun. White light is coming. Let's say somehow I have built the sun in the laboratory. This is the white light. This is the white light. This is your sun. This is white light. And then what? And here is the sample. Here it is your sample. Sample is present. This is your monochromator. What does it do? Let's say I know at which wavelength or what wavelength I want. At which wavelength this sample will going to absorb or I want to just pass only one wavelength at a time. So this monochromator will select that wavelength. Let's say I am like I don't know how many of you know about this absorption spectrophotometer instrument. So as I have already shown you my data is this. See, I have started from like 200, 40, 30 till 500 or 550. Like full range from here till here, right? Which means that the source will be having all the lights. Source will be having all the lights, which means that I need something to select only one wavelength at a time. Otherwise, all the wavelengths will go to the sample directly and excite the sample. So that is why this monochromator comes into the picture and it will select only one wavelength at a time. Let's say right now, just when I am scanning from, so let's say I have given only one wavelength should be, or two nanometer gap bit. So yeah, 1 nanometer gap. So it will like from 250 nanometer to 251 to 253, just like that. So only 250 nanometer wavelength is passing. Then 251, then 253, just like that. If this monochromator will not be there, what will happen? From 250 nanometer to 550 nanometer, all the wavelength, all the light will pass and excite the molecule. But I don't want that. That is why this monochromator comes into the picture. I hope it will be clear. See, it is also written here. Selective narrow wavelength band. So this is the correct answer. Increase light intensity. No, no way. Detect transmitted photons. It is not the detector. Eliminate detector noise. No. I hope it will be clear to you. Okay, moving to next question. A major limitation. Okay, screen is not changing. It will change after some time, probably. We are seeing photo multiplier tube. Because I'm also seeing, but I need to. Okay, question number 8 is there. Yeah, yeah. This. A major limitation of single beam spectrophotometer is. So, have you guys read the instrument, watch the instrument, the video of this instrumentation of absorption spectrophotometer? Lavanya have studied this. So this one is in the screen. You are seeing 8 or 7 question. I guess you are seeing 8. So it is double beam spectrophotometer, and in 7 you are able to see this. This is a single beam spectrophotometer. Single beam means the light is going through the monochromator and exciting the sample, as you can see, and it will reach to the detector. But in double beam spectrophotometer, double beam or single beam. What do you mean by double beam and single beam? Single beam means the only one path of the light is there. But double beam spectrophotometer means now somehow we have adjusted or build the instrument in such a way that it will split the light in 50-50. So there are two parts of the light. That is why double beam. Two beams are going. Hmm. So major limitation of single beam spectrophotometer is anybody would like to answer? Answer is C, fluctuation of lamp intensity. But we have not discussed anything about the lamp intensity with time. What does that mean? You can see the graph also there. But anybody would like to add anything? Suraj. It simply means that this is the bulb or the light source. Light source is not constant all the time. It The intensity of the light source is not constant all the time. Let's say today morning, tomorrow morning I'll go into the lab. I want to perform an absorption. Uh, I want to take the absorption. So I have gone to the lab and I have taken the absorption, collected the data. Then let's say I am done with the data. Then after 3 days, let's say on Thursday, I again go to the lab. Oh, my data was not correct, or I want to repeat my uh, data because for publication we have to repeat at least 3 to 4 times. Number of photons versus radiant power. Okay, but we are not going there anyway. Anyway, so let's say I am going to. Uh, I want to repeat the my this data because for publication I need at least 3 to 4 times to repeat the data. But that time the intensity, let's say all the 3 times. What do you think? The intensity of the lamp will always be the same in the instrument because everything has a lifetime. So let's say you have bought the instrument today itself, and after 1 year, what do you expect? Expect the absorption spectrophotometer only. What do you expect? The intensity of that lamp, this lamp, light source, will be same after a year also. It will change because the lifetime of the lamp is also will going to come down because everything has lifetime. No, otherwise I have just bought the this absorption spectrophotometer once in a lifetime and set up the lab. That's it. I'm done with the absorption spectrophotometer because the lamp will be lifelong. But it is not the case. So that is why the intensity will change. So in this, in question number 7, here, see this graph. If this is your lamp, this is your lamp, and it is changing with time. If it is changing with time, how much you are confident that that the absorb OD absorbance is correct? Because the intensity and also I am going to write in another form. Log I0 by I. So this is white light, this is I0. And after this it will be, here it is detector, this is I. So tell me, if this I0 is going to change and the absorbance is directly related to this, directly proportional. So if the intensity of the lamp is changing day by day or after 6 months or after 1 year, then this is the same sample, it is not damaging like the degrading sample is fine for 1 year. There are samples which will be remain like good, like not degrade for a year, at least a year or more than a year. There are some stable compounds and molecule will not going to degrade anyway. This is the same sample I have taken today, the absorption data, and after a year in the same instrument. So according to this single beam spectrophotometer, if the light the intensity of the lamp source, this today is higher, after a year it will be low, so I0 will be low, right? This I0 intensity will be low. So if intensity will be low, which means absorption will be low of the same sample, and sample is fine. So that is the problem. That is the problem in this instrument, single beam spectrophotometer. So what is what is better? That we have to split that light into uh, two parts, like 50-50. So for one, just to normalize, like at this point of time, what is the intensity we are getting from the lamp? That is I0. Doesn't matter. Even if I'll take uh, absorption of the same sample today or after a year, because I will be going to normalize that. I will be going to normalize that. Okay, because I will going to normalize that because every time I'm measuring this I0, so then it will be no problem. And this is your sample. Here, after the absorbance, whatever light will be absorbed and transmitted light, let's say I0, no I. So that is why this double beam spectrophotometer is better than the single beam spectrophotometer. The answer is fluctuation of lamp intensity with time. And in the class, sir also made this, that the intensity, let's say if intensity of the lamp, that is what I was also saying, with time, this is time, let's say this is time in hours, second or years, intensity of the lamp is constant, then there is no problem. Then there is no problem. But intensity of light is not constant. Of let's say it's going down, up, or whatever it is happening. Let's say I have taken data at this point, then the intensity will be high, absorption will become high. Let's say one day I'll go and I have taken data at this point, at this time, the intensity will be low, absorption will be low. I thought, oh, I think I have the concentration of the sample is low, but it is not the case. It is only because the length of the intensity is not constant. Anyway, and so this is correct. That is the major limitation of the single beam spectrophotometer, and poor wavelength resolution. No, resolution is done by which instrument? Which we have already discussed. Tell me. Resolution of the wavelength done by which instrument? Not the instrument, which part of the instrument? Yes, it is by the manochrometer. And B is inability to measure the absorbance. No, it will be measuring. That is also not correct. Absence of a monochromator. No, monochromator is there. So option C is there. I hope I have made my point clear till now. If you have any doubt, ask me. I'm moving to another next question. Okay, next question is, oh, this is 10, 9. Question number 9. The fundamental physical principle behind the operation of a PMT, photomultiplier tube. How many of you know what is photomultiplier tube? I guess nobody knows. Anyway, so PMT is PMT is a photomultiplier. This is the detector. This PMT photomultiplier tube. So how it works, I'll tell you little bit, not the advanced part of it. So let's say here, after the excitation, selecting the monochromator, splitting your intensity in 50-50, I0 and I is detected. These are detectors. These are detectors. How they are performing? That light is coming from here to this window, from this window to the photocathode. So it will eject the photon from here, and these two photons will come there, and so on and so forth. And here is a we will measure these photons in the form of this signal, which I have shown you by this data. Whatever you are seeing this, okay, this data, whatever you are seeing in your screen, these electronic signal will be, you are able to see on your screen. So now tell me, how many of you know the photoelectric effect? Tell me, how many of you know photoelectric effect? Okay, Lavanya knows. Einstein got the Nobel Prize because of this only, photoelectric effect. So this PMT work on the basis of photoelectric effect, because these electronics, this incoming photons are coming to this photocathode and eject the electron. So basically photoelectric effect is, and photon is coming, this is your surface, metal surface, let's say. So there is a threshold energy. So the energy of the photon should be higher than that threshold energy, then the electron will eject from here, from the surface of the material. So that is the photoelectric effect. I am telling you very layman language, so you have to just go and read a little bit about it. You will be able to understand it. It is not a big deal, right? So this PMT work on the basis of this photoelectric effect. Fine. I'm moving to another question. Next question. Oh, I'm not able to see my screen. Okay. So a molecule that shows solvent dependent color change is called. What does that mean? That when change, let's say you have one sample that I have told you one dye, no, I am using CPM in one of my data somewhere. Oh, I've also forgotten where was my data. Yeah, this one only. Here CPM is written, no, 395 CPM is there. This second peak at around 395 or 400. So let's say this CPM is I'm dissolving the CPM molecule. This is a small molecule. So let's say I'm dissolving this molecule in water, and the same amount of the molecule in the same volume in methanol, then in glycerol, let's say, and in astronitrile, in DMSO, in another, I mean, different series of solvents. So how the property of the absorption or emission will change based on these solvent. So question is asking that only. A molecule that shows a molecule that shows solvent dependent color changes is called solvatochromic molecule, which means that depending on the polarity of the solvent, the color of the fluorophore will change, or the absorption or emission will shift. That is the solvatochromic molecule. So option C is correct, and just before the option C, it is written there: the solvatochromic molecule are the dye that changes color based on the polarity of their surrounding solvent, driven by the differential stabilization of ground state and excited state. They typically feature electron donating and withdrawing groups connecting via a conjugated system, making them an excellent indicator for solvent polarity, microenvironment analysis, sensing, and other stuff. Richard Riker dye, and this we use daily, Riker dye. Anyway, so this is the idea. And to explain other molecule, fluorescogenic molecule, photochromic molecule, and phosphoruscent molecule, I have written the definition for you. So fluorogenic molecules are the non-fluorescent or weakly fluorescent compound that become highly fluorescent upon chemical reaction. So these are called the fluorogenic molecule, like binding to target, like RNA or something. So then they will fluoresce. So they are fluorogenic molecule. And next one are phosphorescent molecule are luminescent compound that absorb light of an UV and re-emit it over an extended period, millisecond to hour, via spin forbidden transition from triplet state to a singlet ground state, often containing heavy metal. Anyway, this is the phosphorescent molecule, which means that from going from S0 to S1, they'll again go to T1 triplet state, then they will fluoresce. So it is like that the lifetime of this molecule is little bit higher. And photochromic molecules are the substance that reversibly change color or optical property when exposed to a specific wavelength of the light UV, undergoing a structural change. So these molecules are, I have given the photochromic reactions, which means let's say there is a this these if you know that the photoisomerization reactions, there is one isomer. If you give the particular light, at which the structure or their isomerization will change. Just like here, the photoisomerization, by giving some light, I'm not able to see. I think it is visible light. So it will change its molecule is changed. Basically, this double bond is already changed here. It is broken, and after you this remove the light, they'll again will go back to the previous the reactant. So these are the photochromic molecule. I hope you got the idea, because just read a little bit. If you have any doubt, ask me in the next class, or if you have right now any doubt, ask me. I've just given you, because these are just some kind of definition, so I don't think there is much to explain. So anyway, but if you have any answer or any question, just ask me. Okay, I hope there is no question. Okay, this is previous year week 0 assignment. I think you have not seen this assignment. More or less, same kind of questions are there. Same kind of question are there, but I have just because I have the access, so I have taken this for you. So in the next class, if you find this class is like I'm going little bit slow, I can be fast because but this is our first class, so that is why I was going little bit slower so that it we can build a base, strong base, then we can speed up little bit. And you can find these lectures and video in my YouTube channel. Also, there is a weekly log sheet. I think they will share with you, or maybe already shared with you. You can watch this recorded video also later on and find this file also, PPT and video. Anyway, so the next question is, what is the spectroscopy? At this time, somebody wants to join. Subhajit Datta. Anyway, so what is spectroscopy? This question I think we have already studied, that it is the spectroscopy is the study of interaction between radiation, light and matter interaction. So option B is correct. Spectroscopy is the study of interaction between matter and electromagnetic radiation. That I have already discussed, so there is no problem. Second question is, what is the purpose of a spectrometer? So for this question, I have given my data here. Basically, any spectrometer is any. I have given the data of the spectrophotometer, which means which measure the absorbance. There is another spectrometer which is spectrofluorometer, which absorbs the emission. So this spectrophotometer is absorbs the absorption versus wavelength. So the purpose of this spectrophotometer is to measure the light intensity as a function of the wavelength. So this is the light intensity here, and this is the wavelength versus the wavelength. Of course, I have normalized this data, because normalized means the highest peak of the my data is 1. Here, this is. So this is for me, my data was there, so I have just plotted there. No problem. So I guess it is fine. It is very simple and moving on. Okay, you guys are not able to see. There's a lagging. Anyway, which region of the electromagnetic spectrum is used in UV visual spectroscopy? So this is the full electromagnetic spectrum, and around 400 or nanometer to 800 nanometer. This is the spectrum which we can see from our eyes. So this Vivgyor, violet, indigo, Vivgyor, green, yellow, orange, whatever it is, and red. So answer would be, what would be the answer? Infrared, microwave, X-ray. So infrared is higher wavelength, microwave is higher wavelength than infrared, and X-ray is higher in energy. So we only see which region of level is used in EV visual spectroscopy. Of course, visual and ultraviolet. There is no problem, right? Moving to this is lagging, that is why I have to again. Okay. What determines the energy of electromagnetic radiation? I hope you have know this formula. E equal to h nu, and this formula C C E equal to h nu, C equal to nu lambda. These, so they are interrelated. C is the speed of light. This is frequency. This is wavelength. This is Planck constant. This is energy. This is frequency. So what determines the energy of the electromagnetic radiation? This is Planck's constant. So this is constant. Frequency is left only. So this is the answer. Frequency plus frequency is also related to the wavelength. Like frequency equal to C by lambda. And C is constant speed of light. So they are inversely proportional. So which means wavelength is also determines the, if you know the wavelength, I mean to say, if you know the wavelength, you can determine the energy using this formula. H is constant, C is constant. I am giving you, let's say, 500 nanometer wavelength. Here, let's say this is 500 wavelength nanometer here. What is the energy? Every time I'm changing this slide, it is making my life difficult because I cannot go back to the previous slide. Anyway, so if you know the wavelength 500 nanometer, you can determine the energy. And if you know the wavelength, then you can convert it to the frequency. Then also you can determine the energy because you know the frequency. So that is why both options are correct. And okay, both wavelength and frequency is given here. So answer is D. Both wavelength and frequency determines the energy of the electromagnetic radiation. I hope these questions are, previous year questions are little bit easier, I guess. There's direct. Anyway, next, what is the relation between wavelength and energy of the electromagnetic? Okay, same question. Here, anybody have any problem? If you've not understood, just speak it up. I hope you have seen this formula. Okay? I think everybody is tired after around after 2 hours of listening me. Anyway, so okay, this is the formula only. There E equal to h nu equal to hc by lambda. So energy is inversely proportional to your lambda and wavelength energy. So this will be the answer. Energy wavelength of electromagnetic inversely proportional to each other. This is simple. I hope there is no problem. Next, which spectroscopy technique is used to study electronic transition? This we have already discussed. Okay, this question. Which spectroscopy technique is used to study electronic transition? This is the electronic transition, as you can see in this photo also. Electronic transition means the light matter interaction is there. Light is coming on the surface of the matter, and that matter is going from ground state to excited state, which we can determine using the absorption spectrophotometer. That is what we are discussing since then, since the beginning, from the beginning. Okay, I guess there is no problem. Is it fine, guys? Just say yes. Okay, okay. They are listening actually. I just wanted to know you guys are listening or just online is present, but you're already out of. Okay, Patlika and there. Okay, anyway, next question. Okay, screen is not. Okay, next question is what is, okay, this is the just the definition. What is the chemiluminescence? Chemiluminescence is the emission of the light caused by the chemical reaction. That is the name of the name is also suggesting. Luminescence means it is fluorescing in chemiluminescence because of the chemical reaction. So that is the answer only. Chemical is often called cold light because it produces minimal heat. It occurs when the exothermic reaction generates an electronically excited intermediate that releases energy as a photon upon returning to its ground state. Common in glow the stick and this and this and this. Okay, anyway, this much definition I have given you. Chemiluminescence means there are other example also, but this much you should know because this is the basics course and you have just read the week 1. So later on I'll explain what does mean, what is written here. Exothermic reaction generates an electronically excited intermediate that releases energy or not releases upon returning to its ground state or what is happening. Okay, I'll explain. So there is photo. I have, this is the photo. Okay, you are not able to see, I guess. Okay, cursor you are not able to see, I guess. Okay, okay, because I'm presenting from my this. Okay, keep. Hmm. This picture is telling about the chemiluminescence. This is from Sir's lecture. So option A is correct. This is light emission caused by the chemical reaction. This this much other things you can read it out because this purpose of this class is whatever is your doubt is there you can ask, or I also read this question and then figure it out which one is difficult, which one is okay, you can figure it out by yourself. So I have given effort to those questions where you need me. So this you can just type what is chemiluminescence, you'll get Wikipedia, so you can read it out. Anyway, I'm moving on. Again, slide is not changing. I have no control over my slides. Anyway, which type of luminescence is responsible for the glow of fireflies? This is bioluminescence is responsible for the glow of the fireflies. Okay, so bioluminescence is these are the photographs you can see. Jellyfish, this jellyfish. This is the sea. There are, you just type the luminescence response, this bioluminescence, chemiluminescence, photoluminescence, triboluminescence, and you will see the beautiful pictures there. And also this bioluminescence, this what we call in Hindi, jugnu. This is jugnu. In the night, we used to see this. Okay. So next question. Okay. So the which type of luminescence is glowing the fireflies. So the bioluminescence. is responsible for glow of the fireflies. The bioluminescence is the natural biochemical emission of the light by living organisms created when the molecules luciferin react with oxygen, often called the enzyme luciferase. Anyway, you can read it out. Next question is, which spectroscopy technique is commonly used to study the luminescence property? Luminescence, I mean the fluorescence. So the common technique is fluorescence. Actually, these two are very common, but in the context of this is written which spectroscopy technique is used to study the luminescence, which means they are asking about the fluorescence spectroscopy. It's commonly used to study the luminescence. Means after the absorption, the the, the fluorescence of the material or matter can be which technique can be used to see that. So this is the fluorescence spectroscopy. Next question, what does the fluorescence spectroscopy primarily study? This is also simple absorption emission of the light by the molecules. So fluorescence is a technique that measures the light emitted from a sample after the absorption. And the lamp we have already discussed, they are having ultraviolet or UV visual excitation source. So this excites to higher electronic energy state. It is a highly sensitive, selective and non-destructive method to identify and quantify the fluorescent compound, often utilizes stochastic whether emitted light is lower energy, longer wavelength than object. Anyway, so one thing I can tell you from both the assignment is that assignment uh, of week 0 of this year was pretty good, and previous year was little bit easier, I would say. Anyway, in the next class, now I wanted to actually solve this week 1 also. I have prepared the slide because week 1 of previous year also, week 2 is also there. Anyway, okay, now tell me, is there any doubt? Ronak, Sagun, Suraj, Subhajit, Patlika, Shivam, others have left. Any doubt from the week 1? Were you able to solve all the questions? All 10? Okay. So give me the feedback. How was the class? Of course, it was slow, but tell me. It is first class, so no, no, just not, not to impress me, not to sugarcoat. Just I want to learn because you will be benefited from your experience, like how you have felt. So in the ha, so that is why that is what I wanted to do actually. And the next class I'll speed up little bit because first class is always like the slowest class, I would say. And what about Suraj? It is helpful, Patlika. Thank you. What about Suraj? Suraj and Sagun, Subhajit, tight help. Yeah, yeah. Come in the next class also. Then we will speed up and solve the question also. These assignment 1, 2, other weeks assignment, previous year assignment. And if you have any doubt, uh, ask me in the next class. And please join. Sunday 4 to 6 p.m. So I am ending this session now for now. We'll meet you next week. Thank you for joining.